Now we go to next insurance, which is a continuous RM1 M-year deferred whole life insurance on X. Provides a payment of RM1 only if the insured dies at least M years after time of issue. So there is a deferment for M years. So from X to X plus M, the insured must survive. And then after M years, if the death happen, the insured will receive payment of RM1. If he dies before M years, there is no payment will be given. So X plus T, the age of death, or T, the time of death, must greater or equal to M years. The benefit function. So if death happen between 0 to M years, so no payment will be given. However, if death happen at T equal to M or greater than that, so the benefit will be equal to 1. So the Vt is equal to V, the power of T, which is E negative delta T for T greater than or equal to M, and Zt is Vt times Bt. So Vt times Bt, Bt is 1. So we get Vt for T greater than or equal to M. Now we can find the net single premium, which is expected value of the present value. So this is how we write down the notation. So X is for the age and M is for the deferment years. And we have bar because it is continuous. So we have to integrate from M to infinity. Since it is whole life, the upper bound is infinity. So we're starting from M because the benefit only paid starting from M years. And then we have two components here, Zt and Gt. So Zt is Bt times Vt. So in this case, Bt is equal to 1. Therefore, Zt is equal to Vt. And the Gt is the Tpx mu x plus T. It is the PDF. So alternatively, we also can write down the deferred insurance as this is for whole life from 0 to infinity, and this is for term insurance from 0 to M. So for this case, for the term insurance for M years, the death must happen from X to X plus M. That's why we also can use this formula, whole life insurance minus the term insurance for M years, to get the deferment for M years. Second type of deferment is a continuous RM1 M year deferred and year term insurance on X. Just now we look at whole life insurance case. So now we look at term insurance case. It provides a payment of RM1 only if the insured X dies at least M years after time of issue but less than M plus N years. So the death must happen between M to m plus n years. So if death happened before m years, no payment will be made. And if death happened after m plus n years, no payment will be made as well. So the death must be happen in between m to m plus n to get the payment of 1 ringgit. So it means that the insured must survive until X plus M years. So this is actually, we also can write down in terms of this one, MEX. So MEX is the pure endowment, whereby the insured must survive to get the benefit. So MEX is equal to VN NPX. So the benefit function for this case, the death must happen between m to m plus 1 to get 1 ringgit. And the discount function is VT at m to m plus n. So the ZT is BT times VT. So this is how we write down the notation. So it is a term insurance as the previous one. We just plus on the deferment years. Or we also can write down in terms of whole life, but until we have to add on the n years here. Since we have to survive until m years, so here it is pure endowment times the term insurance for starting from X plus M for n years. So if we draw the timeline, X, X plus M, and X plus M plus N. So for this case, the term insurance from each X to M plus N years. So the insured must die between X to X plus M plus N years. So this is for term insurance for M years, meaning that the insured must die between X to X plus M to get the benefit. Therefore, from X to X plus M plus N minus X to X plus M. So the rest is from X plus M to X plus M plus N. So C is a continuous 1 ringgit M year deferred N year term endowment insurance on X. So this is for endowment case. Provides a payment of 1 ringgit if the insured X dies at least M years but less than M plus N years after time of issue, or a payment of 1 ringgit at the end of M plus N years if the insured survive at least M plus N years. So endowment, as you know, we have two kind of benefit. Whether first, the benefit if survive until N years, or the second one is the benefit of death. All the deferment case, if the death happen before M years, so there is no payment at all. So first case is death payment for 1 ringgit if it happens between M to M plus N years. So the insured will get 1 ringgit. If let's say he still survive until M plus N years or more, So he will get the payment of surviving. So this is for survive, and this is for death payment. So endowment, we have two kind of benefits. So the benefit function, 1 ringgit if die happen between M to M plus N, and 1 ringgit if he still survive after M plus N years. So the discount function is Vt, V the power of t, if death happen between M to M plus N. However, the discount function become V the power of M plus N if he still survive until t years or greater. So the Zt is the Bt times Vt for these two cases. So the NSP, we can write down like this. So this is endowment notation. So we just plus the deferment years. Actually, this is for term, and this is for pure endowment. So for endowment case, it is the combination of term insurance and pure endowment. So term insurance, if the death happen before M plus N years. So the pure endowment, if the insured survive until at least M plus N years. So the difference between the endowment previously is just the deferment years. So for pure endowment, it is VN and PX, because it's just considered for the surviving. Let's try example 5. So first, we look at the information given. So it is a 5-year deferred whole life insurance, and the force of mortality, the mu is equal to 0.04, and the delta, for the present value function, is 0.10. So calculate the expectation and the variance. So it is whole life insurance. So the upper bound is the infinity. So we start from M, since the benefit will be given only the death happened after M years. So we have two components to calculate the expected value. So Vt is for the discount function, and Gt is the PDF or TPX times mu x plus t. So in this case, the force of mortality is constant. So we use constant force for TPX mu x plus t, which is E negative mu t times mu. So we substitute the values inside. So this is for E negative delta t, and this is mu, since the mu is constant. Then we solve for the integration, and finally we get 0.1438. Now we want to calculate the variance. So first of all, we find EZ squared t. So for this one, we use 2 delta t. So E negative 2 delta t for Z squared t. So the rest is same. Then we solve for the integration. So we get 0.0502. Then we can find the variance. So this is EZ squared t And this is the NSP, the squared for NSP. And we get 0.03. Let's try example 6. So given that t, the time of death, has a uniform distribution on the interval 0 to 100 minus x with delta equal to 0.05, and calculate the whole life insurance, and actually we have deferment here. 20 years for deferment. So M is 20, X is 20 as well. So uniform distribution actually is De Moivre's law. The De Moivre's law comes from the uniform distribution. So for uniform distribution, we have two parameters, A and B. So this is how we write down the PDF, 1 over B minus A. So A and B is the interval. So A for this case is 0 and B is 100 minus X. So this is De Moivre's law. So GT is 1 over 100 minus X minus 0. So then we can integrate the GT and the VT. So this is VT and this is GT. So GT here follows De Moivre's law. So 1 over omega minus X. Or we can straight away taking from this PDF. For the uniform distribution is 1 over B minus A, where B minus A is this interval. Then we solve for the integration and we get 0.08739. Alternatively, we can find this problem using this formula, which is whole life insurance minus the term insurance, like we discussed previously. So first we find the values for whole life insurance, then we find the NSP for term insurance. So we solve the integration and we substitute the values and we get 0.08739. So same as the first method's answer. Now we look at exercise. So this exercise is about term insurance. For the case of increasing benefit, because the benefit is equal to E0.05t. So in example, we use the benefit equal to 1 ringgit. So the constant. So it is the De Moivre's law, since Lx is equal to 100 minus x and the omega is 100 and it is 25-year term insurance. So N is equal to 25 on insured age 40. So X is equal to 40. So first we determine the BT and VT first to find the present value ZT. So the BT is E0.05t. It is increasing function, and since it is the term insurance, so the payment only will be made if the death happened for 25 years. If the death happened after 25 years, so the benefit will not be given. So this is the discount function, and the ZT is VT times E 0.05T. So we can solve the integration. So this is De Moivre's law. So VT is E negative delta T, since the benefit function is E 0.05T instead of 1 ringgit as the previous example, and this is GT. So since the BT is not a constant, so we have to integrate the BT as well. So we solve for the integration. So e to the power of 0 become 1. So we integrate constant, it becomes t. And we get 5/12. So let's say we want to find the variance. So we have to find ez squared t first. And we have to square the e negative delta t times bt. So this is ZT. So we have to square the ZT. And we get 1 as well, because 1 to the power of 2 is 1. And this is for De Moivre's law, 1 over omega minus x. And finally we get the variance is 35/144.